For centuries, humanity envisioned a static cosmos revolving solely around our planet. Yet, the universe is anything but still. Every atom, every star, every galaxy is engaged in a complex, ceaseless dance, propelling us through an unimaginable cosmic ballet. This journey begins not billions of light-years away, but right here, on our own spinning world. Our familiar day and night are direct consequences of Earth's rotation. This colossal sphere, over 12,700 kilometers in diameter, spins on its axis at approximately 1,674 kilometers per hour at the equator. This constant, fundamental motion provides the rhythm of our lives, dictating the rise and set of the sun. Beyond its daily pirouette, Earth embarks on an annual 940 million kilometer orbit around the sun. We hurtle through space at an astonishing average speed of 107,000 kilometers per hour. This grand celestial journey defines our years, our seasons, and our very concept of time. But the sun itself is far from stationary. It, along with our entire solar system, is gravitationally bound to the Milky Way galaxy, orbiting its central supermassive black hole, Sagittarius, a star. This galactic journey is incredibly vast, taking approximately 230 million Earth years to complete a single revolution. Our sun travels at a blistering speed of about 828,000 kilometers per hour relative to the galactic center. To put that into perspective, it's fast enough to cover the distance from Earth to the Moon in about 27 minutes. This astounding velocity is a testament to the colossal gravitational forces at play within our galaxy. Our solar system doesn't just orbit the galactic center, it also bobs up and down like a horse on a carousel, crossing the galactic plane roughly every 30 million years. This vertical oscillation is a gentle undulation within the vast disk of the Milky Way, influenced by the galaxy's gravitational field. This vertical motion is driven by the gravitational influence of the galactic disk itself, acting like a restoring force. As our solar system moves above or below the plane, the combined gravity of the stars and gas pulls it back towards the center, causing this distinctive oscillation. Observations reveal that the Milky Way's outer regions rotate much faster than expected based only on visible matter. This phenomenon, known as the galactic rotation curve, is strong evidence for the existence of dark matter, an enigmatic substance that interacts only gravitationally. Dark matter forms a vast, spherical halo enveloping our galaxy, extending far beyond the visible spiral arms. It exerts a crucial gravitational tug, preventing stars and gas clouds in the galactic outskirts from being flung into intergalactic space by centrifugal force. Our solar system is not an isolated entity within the Milky Way. Surrounding us are countless other stars, all moving with their own unique velocities. The sun is part of a local stellar neighborhood where stars drift past each other, constantly reconfiguring the local stellar landscape. These individual stellar motions are complex, influenced by localized gravitational perturbations from nearby massive stars or stellar remnants. Over vast timescales, these seemingly small nudges can significantly alter a star's trajectory within the galaxy. Beyond our Milky Way lies a cosmic dance on an even grander scale. Our galaxy is not alone. It is gravitationally bound to Andromeda, our nearest large galactic neighbor, forming what is known as the local group of galaxies. The Milky Way and Andromeda are currently hurtling towards each other at approximately 110 kilometers per second. This inevitable collision, billions of years in the future, will not destroy, but rather merge our galaxies into a new, larger elliptical galaxy, often dubbed Milkomeda. This gravitational attraction dominates the local group, binding our galaxy, Andromeda, and about 80 smaller dwarf galaxies into a single cosmic entity. Their collective motion is a ballet of mutual gravitational pulls and pushes. The motion of the triaxial triangulum galaxy, M33, the third largest in the local group, is also affected by this dynamic. Its trajectory suggests it might be orbiting Andromeda, or perhaps has even experienced a close encounter with the Milky Way in the cosmic past. Understanding these intergalactic movements provides crucial insights into the distribution of dark matter within the local group. The gravitational tugs observed cannot be explained by visible matter alone, further solidifying the dark matter hypothesis. As we zoom out further, we see that the local group itself is not static. It is being pulled towards a massive concentration of galaxies known as the Virgo cluster. This galactic metropolis is home to over 1,000 galaxies, forming a powerful gravitational well. Our local group is moving towards the Virgo cluster at approximately 480 kilometers per second. This motion is not a simple direct path. It's a bulk flow, an accumulated drift influenced by multiple gravitational pulls across vast cosmic distances. This supercluster of galaxies, stretching across hundreds of millions of light-years, is our grander cosmic home. It's an intricate network of galaxy clusters and filaments, like a vast, pulsating brain, all influencing each other's trajectories. The movement within Laniakea is often described as a valley of gravitational attraction. Galaxies flow towards the region of highest density, much like water flowing downhill, shaping the peculiar velocities we observe. Peculiar velocities are the deviations of galaxies' actual motions from the smooth expansion of the universe. They are the local variations, the gravitational tugs from nearby clusters and voids that add a distinct, personal signature to each galaxy's cosmic journey. While gravity pulls matter together, a mysterious force known as dark energy is pushing the universe apart. Discovered in the late 1990s, dark energy is responsible for the accelerating expansion of space itself, fundamentally changing our understanding of cosmic motion. This accelerating expansion means that distant galaxies are not just moving away from us. The very space between us and them is stretching. It's like dots on an inflating balloon. The dots themselves don't move, but the surface thereon expands, increasing their separation. This expansion means there's no central point from which the universe expands. Every point in the universe can be considered the center of its own expansion, with all other points moving away from it. It's a truly isotropic and homogeneous expansion on large scales. Hubble's law, formulated by Edwin Hubble in the 1920s, quantitatively describes this expansion. The farther away a galaxy is, the faster it appears to recede from us. This relationship is a cornerstone of modern cosmology and our understanding of the universe's dynamics. The redshift phenomenon, where light from distant galaxies is stretched to longer, redder wavelengths, is our primary observational evidence for cosmic expansion. It's similar to the Doppler effect for sound, but applied to light waves in an expanding universe. Dark energy, the mysterious force behind accelerating expansion, behaves unlike any known matter or radiation. Its existence is inferred from cosmological observations and is currently the biggest enigma in astrophysics, shaping the ultimate destiny of all cosmic motion. One of the leading theories for dark energy postulates it as a cosmological constant, an intrinsic property of space itself with a uniform density throughout the universe. This constant energy density would explain the smooth and accelerating expansion we observe. The implications of accelerating expansion are profound. Eventually, galaxies beyond a certain distance will recede faster than the speed of light due to space expanding, effectively moving beyond our observable cosmic horizon and becoming forever unreachable. Our planet's journey through space isn't just about local astronomy, it's also about our motion relative to the oldest light in the universe, the cosmic microwave background, or CMB. This ancient radiation is the afterglow of the Big Bang, filling all of space. Even against this uniform background, we detect a subtle asymmetry, a CMB dipole anisotropy. This faint hot spot and cold spot across the sky is a direct measure of our solar system's velocity relative to the universe's average background rest frame. This CMB dipole indicates that our local group is hurtling through space at approximately 620 kilometers per second in a specific direction. This astounding velocity is a composite of our galaxy's motion and the pull of larger-scale cosmic structures. Much of this motion is attributed to a massive gravitational anomaly known as the Great Attractor. Located in the direction of the Centaurus supercluster, this immense concentration of mass pulls our local group and countless other galaxies towards it. The Great Attractor is not a single object, but a supercluster of superclusters, an incredibly dense region of the cosmic web. It's the ultimate cosmic drain, drawing in everything within its powerful gravitational reach, including our own Laniakea supercluster. Conversely, other regions, known as voids, are almost empty of galaxies. These underdense spaces exert a kind of gravitational repulsion, pushing galaxies away, further contributing to the complex bulk flows we observe. Gravity, the most familiar of the fundamental forces, is the primary architect of cosmic motion on large scales. It's the invisible hand that shapes galaxies, binds clusters, and orchestrates the grand cosmic ballet, dictating the dance of gravitational attraction. Inertia, a fundamental property of matter, ensures that objects in motion stay in motion unless acted upon by an external force. In the vacuum of space, this means planets, stars, and galaxies will continue their trajectories almost indefinitely, absent significant gravitational nudges. Einstein's theory of general relativity revolutionized our understanding of gravity, not as a force, but as a curvature of spacetime caused by mass and energy. This curvature dictates the paths of objects, meaning they are simply following the shortest path in a curved geometry. Dark matter, while not directly observed, reveals its presence through its gravitational effects on visible matter. It acts as an invisible cosmic scaffolding, providing the extra gravitational pull needed to hold galaxies and galaxy clusters together. Measuring these vast cosmic distances and motions is a monumental task. Astronomers rely on a cosmic distance ladder, a series of overlapping techniques, each building upon the previous one to reach farther into the depths of the universe. Parallax, the apparent shift in an object's position due to the observer's change in viewpoint, is the foundational rung. For nearby stars, we measure this tiny shift as Earth orbits the Sun, providing direct distance measurements. For greater distances, astronomers use standard candles, objects with known intrinsic luminosities. One such beacon is the Cepheid variable star, whose pulsation period directly correlates with its true brightness. Perhaps the most powerful standard candles are Type Ia supernovae, the explosive demise of white dwarf stars. These stellar explosions reach a consistent peak luminosity, making them visible across billions of light years. By comparing a standard candle's apparent brightness to its known intrinsic brightness, astronomers can calculate its distance. This is much like knowing the wattage of a light bulb and how dim it appears. The dimness tells you how far away it is. Gravitational lensing, where massive foreground objects bend the light from background galaxies, acts like a cosmic magnifying glass. This distortion provides another powerful method to probe the distribution of mass, including dark matter, and measure distances. The universe's dynamic nature is not merely a scientific curiosity, it profoundly shapes our understanding of existence. For millennia, humanity yearned for order, for a fixed point in the cosmos. Now we embrace the grand, restless flow. Our sense of stability is an illusion woven by the immense scales of time and distance. What feels eternal on Earth is but a fleeting moment within the cosmic dance, where galaxies collide and superclusters drift across unimaginable abysses. The expanding universe challenges our intuitive grasp of space. It's not expansion into something, but the very fabric of space itself stretching, carrying galaxies along for the ride, like raisins in rising dough. This cosmic motion means that the universe we observe today is fundamentally different from the universe of yesterday and vastly different from the universe of tomorrow. It is a constantly evolving, living entity. The fate of this grand, restless universe hinges on the precise balance between gravity's pull and dark energy's push. The ultimate direction of our cosmic journey depends on which force triumphs in the long run. One possible fate is the big freeze or heat death. If dark energy continues to dominate, the universe will expand forever, increasingly sparse, cold, and dark, as all available energy dissipates and stars eventually burn out. Another, more dramatic scenario is the Big Rip. If dark energy's influence strengthens over time, it could eventually become so powerful that it tears apart not just galaxies, but stars, planets, and even individual atoms, ripping the very fabric of spacetime. Conversely, if gravity were to somehow gain ascendancy, the universe's expansion could eventually halt and reverse, leading to a big crunch. All matter would rush back together, culminating in an infinitely dense, hot singularity, possibly leading to another Big Bang. Our current scientific consensus, however, leans heavily towards the Big Freeze, driven by the observed acceleration of dark energy. This suggests an ongoing, ceaseless journey outwards towards an infinite, ever-emptying void. The vast emptiness of cosmic voids, those colossal regions between galaxy filaments, further emphasize this outward motion. These are the spaces where gravity has yielded, allowing dark energy to dominate, clearing out regions of matter. The largest known structure in the local universe, the Hercules Corona Borealis Great Wall, composed of a supercluster of galaxies, reminds us of the universe's immense scale and its enduring gravitational influence, even amidst expansion. The existence of these massive structures, like the Great Wall, challenges some cosmological models, hinting at even larger-scale motions or structures that influence our bulk flow in ways we are still working to comprehend. Our understanding of the universe's motion is constantly evolving. New observational tools, like the James Webb Space Telescope, allow us to peer further back in time, revealing the motions of galaxies as they were in the early universe. These observations confirm that even in its infancy, the universe was dynamic. Protogalaxies merged and interacted, laying the foundational movements for the cosmic structures we observe today, a ceaseless saga of growth and evolution. The cosmic dance is not random. It is governed by fundamental laws of physics, from the elegant simplicity of gravity to the enigmatic push of dark energy. These forces sculpt galaxies and orchestrate the universe's grand ballet. The continued refinement of these measurements, particularly of the Hubble constant, is crucial for predicting the universe's future, determining the exact speed of its expansion, and thus, where all this motion is leading us. Every particle, from the minuscule quarks within an atom to the colossal galaxy clusters, is inextricably linked in this cosmic narrative of motion. There is no true rest in the universe, only various relative speeds and directions. Even at the grandest scales, patterns emerge. The cosmic web, a vast network of gravitationally bound galaxy superclusters and filaments, is punctuated by massive, empty voids, demonstrating the larger-scale structure shaped by ongoing motion. These filaments are like superhighways, funneling galaxies towards the dense nodes, the galaxy clusters. This slow, inexorable flow of matter defines the larger-scale architecture of the universe and its dynamic evolution. The precise measurement of these bulk flows, these collective movements of matter, helps scientists map the distribution of both visible and dark matter, revealing the unseen gravitational landscape that governs cosmic motion. Our own local group is hurtling not just towards Virgo, but as part of a larger bulk flow. It is drifting towards a still more distant and massive supercluster complex known as the Shapley Supercluster. The Shapley Supercluster represents one of the largest concentrations of mass in our cosmic neighborhood. Its colossal gravitational well pulls everything within hundreds of millions of light-years, including our corner of the universe. Yet on the diametrically opposite side, there is also the influence of the dipole repeller. This region, likely a massive void, pushes against us, contributing to our overall motion, a push and pull dynamic across the cosmos. When we look out into the universe, we are also looking back in time. Light from distant galaxies takes millions or billions of years to reach us, offering glimpses of their motion when the universe was much younger. This time-traveling perspective allows cosmologists to track the evolution of cosmic motion, from the chaotic mergers of nascent galaxies to the more organized flows of superclusters today, painting a dynamic historical picture. The delicate balance of forces that allow for star formation, planetary orbits, and ultimately life is a direct result of these precise cosmic motions and the interplay of gravity, dark matter, and dark energy across vast epochs. Our very existence on Earth is tied to the Sun's stable orbit within the Milky Way's habitable zone, a region where conditions are just right for liquid water, a consequence of continuous, balanced motion. The cosmic motion also brings about spectacular, albeit slow, celestial events. Galactic cannibalism, where larger galaxies absorb smaller ones, is a visible testament to the relentless gravitational forces at play. Stellar streams, remnants of dwarf galaxies, or globular clusters torn apart by the Milky Way's gravity, are celestial rivers of stars, tracing the gravitational pathways of our galaxy's cannibalistic past and ongoing dynamic. The universe's motion is also a constant source of new discoveries. Gravitational wave astronomy, for example, detects ripples in spacetime caused by the violent mergers of black holes and neutron stars, revealing extreme cosmic dynamics. These gravitational waves provide a completely new sense for observing the universe's motion, offering insights into events invisible to traditional telescopes and opening a new window onto the most energetic cosmic phenomena. The Big Bang Theory itself describes the universe originating from an extremely hot, dense state and then rapidly expanding. This initial, incredibly rapid expansion set the stage for all subsequent cosmic motion. The initial conditions of the Big Bang, including tiny quantum fluctuations, are believed to be the seeds from which all the larger-scale structures and their subsequent motions eventually grew. Even on subatomic scales, particles are in constant motion, vibrating, spinning, and interacting within quantum fields. This inherent restlessness is a fundamental property of reality, extending from the smallest to the largest scales. Understanding where we're going requires not just observing the what, but understanding the why, the fundamental forces and principles that drive every aspect of cosmic motion, from local interactions to universal expansion. This relentless motion means galaxies that are currently visible to us will eventually disappear beyond our cosmological horizon as space expands. Future astronomers will see a much emptier cosmos. This phenomenon, called cosmic acceleration, means that future civilizations, if they exist that far in the future, might deduce a different history of the universe, believing their galaxy to be an isolated island in an unchanging void. The dynamic nature of the universe underscores our own insignificance yet profound connection. We are not static observers, but active participants on a fast-moving, expanding cosmic vessel. Our cosmic address is a complex, multi-layered description of motion. Earth rotates, Earth orbits the Sun orbits the galactic center, the Milky Way moves within the local group is pulled by Virgo and Shapley, and all within an accelerating, expansive universe. The pursuit of understanding this motion has led to incredible technological advancements, from powerful telescopes mapping distant light to sophisticated simulations recreating the universe's evolution. These simulations, governed by the known laws of physics, allow cosmologists to rewind and fast-forward the universe, testing hypotheses about dark matter, dark energy, and the very structure of the cosmic web. Ultimately, knowing where we're going means knowing where we came from. The universe's motion is a continuous narrative connecting the primordial energy of the Big Bang to the complex cosmic structures of today. The vastness of cosmic scales means that while stars orbit swiftly within galaxies, the galaxies themselves drift much slower across the cosmic web, taking billions of years to traverse their titanic distances. The precise choreography of galaxies within clusters, their merging and interactions, reveal how these colossal structures grow and evolve, driven by the relentless pull of gravity over cosmic eons. What does this ceaseless motion mean for life? It means an ever-changing cosmic environment. Our sun will eventually leave its current position in the galaxy, and our galaxy will merge with Andromeda. Planets are pulled by their stars, stars by their galaxies, and galaxies by the cosmic web. This nested hierarchy of motion ensures that nothing is ever truly stationary. The very existence of elements heavier than hydrogen and helium, vital for planets and life, depends on the motion of stars. They forge these elements in their hot cores and scatter them through supernova explosions into the cosmos. Without the internal motions within stars, convection, fusion, stellar winds, these elements would remain locked away, never forming the raw materials for new generations of stars, planets, and life. The universe's motion is cyclical on some scales, with matter condensing into stars and galaxies, then being dispersed by supernovae, only to coalesce again in an endless cosmic recycling. The forces governing motion are not static either. Dark energy's accelerating push appears to be growing stronger relative to gravity's pull as the universe expands and matter becomes more diffuse. This shift in dominance directly affects the universe's long-term future, determining whether galaxies will remain gravitationally bound or eventually be pulled apart by the accelerating expansion. Our perspective on cosmic motion is forever tied to our position within this vast, dynamic tapestry. From Earth, we perceive specific redshifts and blueshifts unique to our particular trajectory. If we were located in a different galaxy, perhaps in a distant void or deep within a supercluster, our perceived universe would appear to move quite differently, challenging our notion of a singular cosmic truth. The universe's motion is the very essence of cosmological research. It's the engine driving discovery, prompting questions about destiny, origin, and the fundamental nature of reality itself. The Big Bang singularity itself, the starting point of expansion, is not a location in space, but a moment in time when all of space was compressed into an infinitely small, dense point. From that singular point, every part of the universe has been moving away from every other part. This fundamental expansion continues to shape the cosmic landscape we inhabit. The concept of the cosmic horizon defines the limits of our observational reach. It represents the maximum distance from which light has had time to reach us since the Big Bang, influenced by the universe's expansion. Galaxies beyond this horizon exist, and they are moving away from us, but their light will never reach us due to the accelerating expansion of space. They are forever beyond our direct observation. The universe's motion is a continuous reminder of its dynamic, ever-changing nature. It is not a static painting, but a living, breathing tapestry where every thread is in flux. This constant movement has profound implications for the search for extraterrestrial life. Planets and their host stars are constantly on the move, reshaping their galactic neighborhoods over eons. The very composition of our solar system, with its orderly planet distribution, is a product of its stable, long-term motion within a relatively quiet galactic neighborhood, allowing for billions of years of evolution. The precise speeds and directions of stars within galaxies help us understand their formation and evolution, where stellar populations have migrated, and how galaxies have assembled over time. The journey of our Sun around the galactic center has seen it pass through different galactic environments, perhaps even denser regions that could have impacted the Oort cloud and cometary bombardments on Earth. Understanding the universe's motion allows us to trace the origins of matter itself, from the nucleosynthesis in the Big Bang to the elements forged in stars and scattered across the cosmos by their explosive deaths. The study of cosmic structures and their intricate movements provides a canvas for testing theories of gravity beyond what can be observed in our solar system, probing the limits of our physical laws. This deep dive into cosmic motion brings home the profound realization that everything, from the smallest to the largest, is interconnected through the flow of energy and the dance of gravity across vast, unimaginable timescales. The thought of our ceaseless plummet through space, caught in a grand, beautiful flow, can be both humbling and exhilarating. It redefines our perception of place and existence. We are not static inhabitants of a fixed planet, but passengers on a celestial vessel, charting a course through an ever-expanding, ever-changing cosmic ocean. Our destination is unknown, but the journey is undeniable. The universe's motion is the rhythm of creation, destruction, and recreation. It is the silent, powerful engine driving the evolution of stars, galaxies, and perhaps life itself across billions of years. Embracing this dynamic reality inspires a deeper appreciation for the intricate physics that govern our existence and the breathtaking beauty of a cosmos that never rests. So where are we really going? We are going everywhere all at once. We are riding the expansion of space, pulled by gravitational wells and orbiting within our galactic home, a complex superposition of myriad motions. Our destination isn't a fixed point, but a continuous journey, a constant renegotiation of our position relative to everything else in an ever-moving, ever-evolving universe. The journey is the essence of cosmic reality. It offers no solid ground, no absolute rest, only the constant, beautiful flow of existence. This understanding transcends mere science. It infuses our place in the cosmos with a sense of wonder, reminding us that we are part of something unimaginably vast, ancient, and endlessly dynamic. The universe is moving, and so are we, a testament to its eternal vitality, its boundless energy, and the profound, beautiful mystery of its endless journey.